Hello. As in real life, or even as processes that happen, everything has to, the initiation of something is the important part of the event. And similar to that, in translation, like in replication or transcription or any of these mechanisms that we have seen, initiation plays a very important role. And we'll have a look at the events and requirements that are essential for initiation to occur. So the initiation would require that there is a mRNA, and the mRNA should be translated. That means the open reading frame that is present in the mRNA should be read, and the reading is done by the ribosome, and what brings in the amino acids are the tRNAs. So the recognition of mRNA is something important. So the ribosome binding site should be there, and there should be the start codon. So we need initiator tRNA and the small subunit to recognize the mRNA and the start of the open reading frame, so that translation can occur. So how does this recognition happen is something has some important details that we need to discuss. So the small subunit, the one that is shown here in the blue, is the small subunit indicated here, and the dark blue are the rRNA molecules that are present. And there are three kind of arbitrary sites, you can say. This is referred to as the A site, and the other ones B site, etc. P site, sorry. This is the A site, this is the P site, and here is the E site. Aminoacyl site, you can say, peptidyl site, P site for peptidyl site, and E for exit site. So the small subunit interacts with the mRNA and be able to identify it. This is especially true in the case with prokaryotes. So the 16S rRNA that makes up the part of the RNA in the small subunit, ribosomal subunit, will be able to base pair and recognize the ribosome binding site. In the prokaryotes, we call it as Schindler-Gerno sequence. So there is the Schindler-Gerno sequence is here, something like AGGAG, and it has the 16S rRNA has a complementary sequence. If we read from 5' direction, we'll read it as CUCCU. So that perfectly base pairs with the Schindler-Gerno sequence, which is the ribosome binding site in the prokaryotic mRNA. And it is also important to note that not all mRNAs would exactly have the same AGGAG. There could be differences, subtle differences in the ribosome binding site, and that determines the efficiency with which initiation can occur. And so while recognizing this, the ribosome binding site at the A site, the ribosome at the 16S rRNA will recognize the ribosome binding site, and there is a spacing between the ribosome binding site here till that of the start codon. The start codon is AUG, and we have about 1, 2, 3, 4, 5, 6, 7, 8. So there is a space between this ribosome binding site and the start codon, somewhere between 6 to 9 bases. In different mRNA, the space could vary between 6 to 9. And again, the spacer also may influence the efficiency with which initiation can occur. So the best option, the best sequence so far determined is AGGAG, which is a perfect match with that of the ribosomal 16S rRNA sequence in that particular locus. So we also need initiator tRNA. Initiator tRNA is separate, and it is the one that recognizes the AUG codon, and AUG when it is in the start of the open reading frame, the initiator tRNA gets N-formyl methionine. So if we have the carboxylic group, we have the amino group, and we have the sulfur containing the side chain, the methionine. So there is a aldehyde group added to the amino group here. So we call it as N-formyl methionine. So this is only added when it is to by the initiator tRNA in the front in the N terminus of the protein, or the first amino acid would be N-formyl methionine, which is usually cleaved off or formulated at a later stage during the translation process. The next important aspect during initiation is there are so many, there are many initiation factors, which we will call them as IF. Here, for example, we have IF1, IF2, and IF3. Similarly, as we go for elongation, we have elongation factors, and when we go that, we will call it as EF. And when we go to the termination, we have release factors there. So basically, we have somewhere around this place, we have the ribosome binding site, and the initiator tRNA, which is present in the P site, that is the peptidyl site, is located within the that is where it is lodged, the AUG there. This is the blue indicates the initiator tRNA charged with N-formyl methionine, and then in the A site we have IF2, that is initiation factor 2 and initiation factor 1. And there is also a factor that is IF3. So we have IF1, IF2, IF3. We have 3 sites. First important thing is, if we have a ribosome, something like this, both small subunit and the large subunit, then the ability for the mRNA to get inside is not possible. So at all times, the free ribosomes should mostly, if not all the times, should be as 2 separate units. At least the 30th subunit should be free, so that it can bind to the mRNA, and on top of it, the large subunit can bind. So to keep these two together, the job is performed by initiation factor 3. It blocks the binding of the 50th subunit onto the small subunit until the initiation factor, the pre-initiation complex is formed. And we have IF1. We have IF1 should be bound in the A site, so that no tRNA is bound here. As we can estimate, the A site has high affinity for tRNA. The shape of the A site fits in with that of a tRNA. And as we understand it, the ribosome, when it is reading the open reading frame, it will have to accept several tRNAs coming from the outside. So in a way, you can assume that the A site has some affinity for tRNAs, because of which there is a probability that the tRNA might come into the A site, and that should be prevented. It should be prevented because say if we have AUG start codon here, and we may have some other codon here. We don't know what that codon would be of the mRNA that is going to be bound to this particular small subunit. So if we already have a tRNA here, say for example, and if it may not match with the second codon here, because we don't know for sure. We know that all open reading frames start with AUG, so initiator tRNA can be here, but we cannot say with the same validity or with assurance or believe that the second codon would be this. It's not fixed. So somehow we need to have all the A site free, so that we will not have any discrepancy with codon anticodon pairing, etc. So IF1, initiation factor 1, is thought to prevent binding of any tRNA to the A site. And then we also have IF2. IF2 is important for bringing the initiator tRNA to the P site. So IF1, IF2, and IF3, they all have their own clear-cut reasons of why they should be there. In the same way, as we proceed, we may not discuss all the aspects of every transcription factor or these translational factors in general, if we call it. But it is important to see why they must be, or we can think of them as if they're not there, what would happen? And that would provide us a good answer for these. I hope we have come across the different aspects of the initiation, and we have seen different factors that are responsible for and their roles as well. And what we have discussed here is more suitable for prokaryotic, or it is about prokaryotic initiation factors. With eukaryotes, there are differences. Say, for example, they have their counterparts, which have their own functions also similar to that of the initiation factors with the prokaryote. Only difference is the eukaryotic ones are much more numerous in number and complexity, and also that we don't know all the details about the eukaryotic systems yet, or the people are still working, or we can say it as prokaryotic systems are better understood than the eukaryotic ones. So that is what about the requirements for the initiation of translation in prokaryotes. We'll see you later. Bye-bye.